Welcome! This is the video tutorial series on the roll-up bond construction technology, presented by Scott Rwanda and the ProEco program. Part 3. The roll-up bond construction process. In this video, we will summarize the roll-up bond construction process in its core elements. We remind you that a comprehensive guide on the roll-up bond construction system can be found at the website www.madeingreatlakes.com. The foundations. Once the location of the building is determined and the site setting complete, the foundations trenches are excavated to a depth predetermined by the structural engineer, according to a combination of soil load-bearing resistance and weight of the building. Stone rubble is one of the most commonly used material for underground foundations, as it's a perfect water and mineral-resistant material, extremely hard and durable. However, according to the nature of the soil, other typologies of foundations can be used. The ground beam. The ground beam is the connecting element between what is built below the ground level and the building elevations. It's a continuous reinforced concrete beam that transfers and homogeneously distributes the load of the bearing walls onto the stone walls of the foundations. The vertical rebars connecting the masonry reinforcements to the ground beam are placed at precisely designed locations as per the structural details before casting the concrete. Before the masonry works can start, the workers select and separate regular bricks from those with deformities, discolorations and superficial damages. Bricks with minor defects will be set aside for secondary works. The bricks are then soaked in water for a minimum of 1 hour before being used. The main reason is to prevent dry bricks from seeping water from the mortar they are laid on, weakening the joints. The roll-up bond walls. The masonry works begin with positioning strings to properly align the walls. Then the first and second courses of bricks are dry stacked to verify the correct arrangement of the bond and measure out the position of doors and windows as well as the total footprint of the building. The works continue with the masonry construction. The first course is typically a solid course where the cavities are filled with an extra brick to increase the stability of the walls. The walls are usually built by masons working in couples, one of each side of the wall, helping each other in the positioning and alignment of each brick. This guarantees a qualitative finish on both faces of the wall at the same time. Cavities are left around the vertical rebars for the vertical reinforcements to be cast every 6th course. To guarantee an accurate 1 cm spacing of the vertical joint between bricks and horizontal joints between courses, short pieces of rebar are interposed between courses and later removed once the mortar is set. Once the level of the horizontal reinforcement is reached, typically every 12 courses and/or in correspondence of windows and doors, the masons fill the wall cavity with discarded bricks in order to create a solid surface where to cast the concrete later on. After the main cavities are filled, the next brick course is built to form a U-shaped channel. Meanwhile, the reinforcement bars are cut and shaped as per design. The rebars are normally 2 per vertical or horizontal reinforcement, with stirrups every 15 or 20 cm. The diameter of the rebars is calculated by the structural engineer. Once they are in place, the concrete then is poured and compacted manually to prevent the brick concealing formwork from being damaged. Let's talk now about the suspended slabs. In order to understand how they are built, we have to analyze them in the context of the load-bearing walls. As introduced in previous video tutorials, the roll-up bond walls are load-bearing walls that do not need additional columns or beams to withstand the various applied loads. Specifically, one prevalent direction is chosen to be the slab-bearing walls. This relieves the wall in the orthogonal direction from additional loads other than their own, allowing for a variety of openings to be positioned along the facade. Positioning openings along the slab-bearing walls is allowed, when sensibly positioned and sized. As we can imagine, the bigger the opening and the higher the strain on the supporting lintel would be. Generally speaking, a standard door opening will not have any impact on the lintel stability. Opening larger than that instead will require additional lintel reinforcements. The load-bearing walls are positioned at a specific distance from each other. This distance is determined partially by the architectural design, but also by the chosen suspended slab technology. 2 examples can be timber floors and max span floors. The span that timber's beam can cover varies greatly, and it's mainly down to the available type and size of beams. As for the MaxSpan technology, the nominal span ranges between 4 and 5 meters, according to the specifications. Timber floors are an affordable solution that can be quickly installed, offers great flexibility in case of modifications, and has good anti-seismic properties due to its light weight. The downsides are limited market availability and the reduced fire resistance and noise insulation. The main features of a tongue and groove timber floor is the natural beauty of the material, its warmth and feel. However, the limited sound insulation make them suitable for interior partition only, rather than for dwelling-to-dwelling partitions. In the process of installation, the beams are positioned at a consistent distance set by the masonry pattern. The result is a seamless integration with the roll-lock-bound masonry and an easy-to-install and modify construction system. MaxSpan floors instead are quickly semi-dry floors built with a combination of hollow clay blocks and reinforced concrete. The major advantages are the relatively lightweight and reduced cost when compared to solid reinforced concrete floors, and they offer sound good proofing and fire resistance. They are suitable, as previously mentioned, for spans ranging from 4 to 5 meters on average, according to the model of hollow clay block chosen among the available ones. The MaxSpan floors can be following two construction processes. The first is a prefabricated one. The MaxSpan beams, also known as MaxSpan ribs, are precast on-site according to the design and specifications of the project. The curing time is 28 days. This means that if the precast activities are planned well in advance, by the time the elevations will reach the first floor, the beams will be ready to be installed. The added advantage of the precast version is also the significant reduction in cost of transportation, reduced scaffolding required, and overall time of construction. The in-situ MaxSpan versions instead sees the beams, reinforcements and clay blocks positioned at the same time over a scaffolding similar to that of a solid slab. The entire slab reinforcement system is completed before the concrete is cast. The pour is then done in a similar way for both the precast and in-situ versions, with the only difference being that for the in-situ MaxSpan slab, the beams and the top screed are cast at the same time, while on the precast version, the top screed is the bonding agent between the dry elements previously installed. The top and bottom finishing works are determined by the available budget and project requirements. The top surface can be left bare or it can be tiled. The ceiling can also be left bare, plastered or concealed by a suspended ceiling. Similarly to the timber beams, the MaxSpan beams are positioned at a consistent distance set by the masonry pattern and connected to waiting rebars previously embedded in the masonry reinforcement. As demonstrated here, the rebars and precast beams interlock before the masonry is built around the connection and the joint is sealed with concrete. When it comes instead to the mechanical, electrical and plumbing installations, the two key elements to consider while working with the roll-lock-bound technology are good planning and smart use of the cavities. The cavity is a great feature that allows to conceal most MEP systems within the masonry without the need of chiseling walls or plastering. It also allows for retrofitting or modifications where necessary. The masonry cavities run vertically, diagonally, and for flexible elements also horizontally. They are however interrupted by the horizontal reinforcements that require provisions within the cast to allow for the vertical communications between floors. When it comes to vertical distributions, both solid or lightweight stairs can be fitted and supported by the roll-lock-bound masonry. The different typologies of stairs have to respond mainly to the architectural design, spatial distribution and accessibility, keeping in mind that they are necessary elements of the design, but they can also occupy considerable portions of the available space. We present here three examples of interior distribution, starting with the stair solution that wraps around the central spine wall. This solution allows to access both single-level and split-level floors. The switchback solution is particularly efficient for split-level that accommodate different floor levels between the front and the rear of the building. Structurally, they rely on slabs or ground floor for support. The third solution is a linear stair aligned with the direction of the floor beam. This is typically the most efficient solution. It can help organize the interior space and can be a decorative element. Structurally, it anchors to the roll-up wall for support. Lastly, the roof construction. The timber or steel structure is firmly anchored to the brick wall by interlocking or inserting the main elements within the roll-up masonry, similarly to the beams of a timber floor. For spans of less than 4 meters, trusses may not be necessary. The spacing between the timber beams is determined by their length, the spacing of the purlins, and the gauge of the iron sheet to be used. The spacing usually ranges between 0.6 and 1.2 meters. The cover is a corrugated metal sheet with a minimum gauge of G28. The specific design of the gutter profile depends on the roof design, the presence of a roof eave, and the rain catchment surface size. We encourage the viewer to visit the SCAT Resources website www.madeingreatlakes.com for detailed information about the technology and more. Thank you.